Welcome to the Explainer. Today, we're going to talk about how a single number, the average, can sometimes, well, lie to you. And we'll see what the shape of our data can tell us about what's really going on with things like balance and inequality.
You know, we hear about averages all the time, right? Average income, average test score, average price of a house. It's just such a convenient, simple number. But what if I told you that sometimes that one number is actually hiding the real story?
Okay, so take a look at this. We've got two teams, Team A and Team B. Now, on paper, they look pretty similar. Both have the exact same average salary, $50,000. But would you say they're paid equally? I mean, look closer. On Team A, everybody makes the exact same amount. But on Team B, whoa, you've got one superstar raking it in, while everyone else is actually making less than that $50,000 average. It's the same average, but a totally different reality.
All right, so here's our game plan. We're going to start by moving beyond the average. Then we'll get into the shape of what's called skewness. We'll look at how the mean, median, and mode are like little detectives. Then we'll figure out how to actually measure the lean, put it all to the test with a tale of two factories, and wrap up by talking about why this whole shape thing is so important.
So, like we just saw with those two teams, if you really want to get the whole picture, you've got to look past that one single number. The average, yeah, it tells you where the center is, kinda, but it tells you absolutely nothing about how everything is spread out, or, the actual shape of the data.
And that's where the hero of our story comes in, skewness. It sounds a little technical, but really it's just a way to measure if something is lopsided or asymmetrical. It tells us if our data is all piled up nicely in the middle or if it has this long trailing tail off to one side.
So, if you want the textbook definition, skewness is when a distribution stretches out more on one side of its peak than the other. Yep, it's all about that lean.
Okay, so let's start with our baseline, which is a symmetrical distribution. Just picture a perfect bell curve, The data's perfectly balanced, there's no lean at all, and the right side is a perfect mirror image of the left. This is what we call zero skew. Now this is where it gets interesting. With the positive skew, most of the data points are kind of clustered over on the left, but then you've got a few really, really high values that are pulling this long tail out to the right. A classic example of this is income. Most of us earn a moderate amount, right? But a few billionaires pull that average income way, way up. And you guessed it, the opposite of that is a negative skew. This time, the tail gets stretched out to the left towards the lower numbers. This happens when most of your data is bunched up at the high end, but a few super low values are dragging the whole thing down. Think about grades on a really easy test. Most students get an A, but maybe a couple of people didn't study at all, and their scores pull that average down.
Okay, so that's what skew looks like when you can see it on a graph. But what if you can't? How can you spot it just by looking at the numbers? Well, the secret lies in the relationship between three old friends: the mean, the median, and the mode. Check out this table. It's got three different groups of data. Now, look right there in the middle, at group 2. See how it's symmetrical? The mean, median, and mode are all exactly the same. But now look at the skewed groups, group I and group 3. See how those three numbers start to pull away from each other? That's our big clue.
So here's the golden rule, the one thing you really need to remember. That long tail always pulls the mean, the average, in its direction. So for a positive skew, those super high values are going to pull the mean above the median. And for a negative skew, those super low values drag the mean below the median. The mode? It just hangs out where the action is, right at the peak.
All right, so knowing if it's positive or negative is a great start. But, in stats, we like to be a bit more precise than that. We need a way to measure exactly how skewed the data is. Are we talking about a gentle lean or a really severe one? And to do that, we can turn to a tool from a guy named Carl Pearson. He was a statistician who came up with this really elegant, super simple formula to put an actual number on skewness.
The logic behind it is actually pretty cool and, kind of intuitive. First, you just find the distance between the mean and the mode. Then, and this is the key part, you standardize it. You compare that gap to the standard deviation, which is just a fancy way of saying how spread out all the data is. The result? A simple ratio that you can compare across different data sets.
And here's the formula itself. It's super straightforward. You take the mean, subtract the mode, and then divide that whole thing by the standard deviation. If you get a positive number, you've got a positive skew. If you get a negative number, you've got a negative skew. Simple as that.
So what do those numbers actually mean? Well, usually, your answer is going to fall somewhere between -1 and +1. A 0, that's perfect symmetry, no skew at all. A number getting close to +1 tells you you've got a strong positive skew. And of course, a number heading towards -1 means you've got a strong negative skew.
Okay, enough theory. Let's get our hands dirty and apply this to a real-world example. Let's call it a tale of two factories.
So here's the wage data for our two factories, A and B. And here's what's interesting. Look at the standard deviation. It's identical. That means the overall spread of wages is the same in both places. But their skewness scores, +0.5 and -0.5, those tell two completely different stories.
Let's look at Factory A. That positive skew of +0.5 is a dead giveaway. The mean wage, the average, is $50, which is higher than the most common wage of $45. So what does that tell you? It suggests that a few high-paid execs are pulling that average way up, while the typical person on the factory floor is actually earning less than the average.
Okay, now let's switch over to Factory B. With its negative skew, the whole story gets flipped on its head. Here, the average wage of $45 is actually lower than the most common wage of $50. This means the majority of workers there are earning more than the average, but a few really low-paid positions are dragging that average down. So, which factory would you rather work at? It's pretty clear, right?
And all of this brings us to the big takeaway, the most important point of all. Understanding skewness isn't just some boring stats exercise. It's about digging deeper. It's about seeing the full, rich story that the data is trying to tell you.
Seriously, the shape of data matters everywhere. In economics, it shines a light on hidden inequality. In finance, it helps you assess risk. I mean, a positively skewed stock might have lots of little losses, but also the potential for a huge, rare gain. In science, it keeps researchers from making bad conclusions based on an average that doesn't really represent their data. At the end of the day, it just makes you a smarter, more critical thinker.
So, we're going to leave you with this thought. The next time you see a headline that talks about the average anything, you'll know that's not the end of the story. For you, it's just the beginning of a much more interesting question. What's the shape of the data?